And for an example, let's consider something we already know. We already know that there is no algorithm to answer the question, does an arbitrarily chosen Turing machine halt on an arbitrarily chosen input? Okay. I'm using the term arbitrarily chosen there because obviously, if you walk up to me with a very simple Turing machine and say a fairly short input, I can probably sit there and I can look at it and tell you whether it's going to halt on that input or not. But human brains are not necessarily limited to working in a straight algorithmic fashion. So there's often things we can prove about specific cases that we would not be able to find algorithms for in the general case. So in the general case, we know that we cannot show whether a Turing machine will halt on a specific input. But think about how Turing machines work. They read those symbols off the tape and then they move, and as they move, they're writing. I can sort of look through a Turing machine to see whether it actually ever moves or not, and whether it actually needs to see a particular input. So here's the question. Is it maybe easier to answer the problem, does a Turing machine halt on empty input? That is, on the string epsilon. And I might as well get this in now so I can copy and paste it later. So does this Turing machine halt on the empty string? Not obvious that this would be, easier, but it might you might sort of suspect in the back of your head that this is an easier problem to solve than saying, does a Turing machine halt on an arbitrary input? We've narrowed it down a bit. Is that enough to narrow things down to actually make that solvable? And the answer is going to be no. That's actually not enough to make this solvable. So we're going to start by reformulating this a little bit as a familiar language problem. So we'll let lambda, or L sub epsilon, be the language set of all strings. In this case, where the strings are these binary number encodings of Turing machines that happen to halt on input epsilon. And what we want to know is that language recursive? Can we decide membership in that language with an algorithm that always halts? And let me propose a way to transform some interesting problems into that. Suppose that I have a recursive Turing machine, which I'll call M sub epsilon. And that it solves that problem. Does the Turing machine halt on empty input? Okay, so M sub epsilon I should be able to treat like a function where I can give it another Turing machine as an input, and it's going to say yes or no, the binary encoding of that other Turing machine is in this set L sub epsilon, or no, it's not in L sub epsilon. That's what I mean by saying I have a way to solve this. So M sub epsilon is the recognizer for the language of all Turing machines that halt on empty input. Now, let me show you that if that were in fact true, so we're going to assume, by way of contradiction, that M sub epsilon always halts. Okay, so that's going to be our assumption. Now I'm going to show you that, in fact, if that were true, I could solve the general halting problem using that machine. And to do that, what I'll do is I'll give a simple sort of wrapper around that machine m sub epsilon. And I'm going to call this wrapper machine prime. And it will take an input x on the input tape. And my m prime is going to start by erasing I'm going to say erasing everything on the tape, but I sort of don't really need to do that. But so I'm going to say what I'm going to do is I'm going to write the encoding of m sub epsilon right? Because I've got m sub epsilon, so if I've got it in whatever form, I can presumably come up with its encoding. Right, the encoding of epsilon, then 111 just to the left of x. Okay, and you should be comfortable enough with Turing machines to realize that, yeah, that shouldn't be real hard. Okay, all I have to do is back up some number of spaces to the left and start writing out that particular string. It's a constant string. We're assuming we already know what that Turing machine m sub epsilon is, so we've got its encoding. You can easily write a Turing machine that's just one state that says write a 1, then write a 0, then write a couple ones, then write another 0, whatever it takes to actually write out that particular binary constant. It's just a constant. Take a whole bunch of states, but we can do it. Okay, that's not a hard thing for a Turing machine to do. It's just tedious, to write out. So I'm not going to try to draw that. But you should believe that we can actually do that. Now, remember, also from your readings and from our discussion last week, that there's this funny Turing machine U, the universal Turing machine. And it takes input of form, a Turing machine encoding, 111, and then whatever your input to that Turing machine is going to be. So we've actually set up an input in the form that the universal Turing machine can process. So let's go ahead and run the universal Turing machine U to simulate the machine m sub epsilon on x. Now, if m sub epsilon always halts on all of its inputs, which we've assumed, right? That's our assumption for this proof. If that always halts, then presumably the simulator is going to always halt as well. So we can trust that that's actually going to halt. And when it halts, it will halt and either accept or not accept. And it will accept if, in fact, X is the description of a Turing machine that halts on empty input. Because that's what m sub epsilon does. So basically, if I then want to solve an interesting problem, I could say, suppose I then run m prime of some arbitrarily chosen Turing machine, 111, some arbitrarily chosen input W. Now what I would be saying is, you will simulate m sub epsilon on M111W and tell me if that machine halts on empty input. Well, this machine doesn't need any input because we've already embedded that input into the X that we're writing out onto the string. So this m prime will halt, saying yes or no, to tell us whether U running on that would halt on empty input, which tells us whether M would halt on input W. And that's the halting problem. Does an arbitrarily chosen Turing machine M halt on arbitrarily chosen input W? So if this always halts, then we can solve the halting problem, even though this only tests for empty inputs. Because this little transformation we did here is easy to do in finite time. It's something a Turing machine can do. So we have transformed, therefore, the problem of solving the halting problem into the problem of solving the halting on empty input problem. Or instead of transformed, we can say reduced. And so we say we have reduced the halting problem to the problem of solving the halting on empty input problem. The biggest trick in doing proofs by reduction like this, okay, is to make sure you go in the right direction. It's very easy to get confused and move in the other direction and say, well, suppose we knew how to solve the halting problem. Could we use that to solve the halting on empty input problem? That would be even easier, right? Because then you just set W equal to epsilon. But that's just reasoning from a false premise. You know, if 1 equals 2, I can prove anything. So if we could solve the halting problem, well, guess what? I can solve all kinds of things given a false premise. Okay, that doesn't tell us anything. What we need to do is you need to start with the thing that you're uncertain about, in this case, the halting on empty input problem, and show that you can use it to solve something that you are certain about already, the general halting problem, or anything else that you know is not recursive.